Okay, yeah, cool. Morning everybody. As introduced earlier on, my name's Tim, and as you may be able to tell, it's not a problem with the loudspeakers now in here. I am from the UK, and so sound a little bit different to James. I've just a little bit of background. So I've been working for Thermo Fisher for almost 20 years now, and exclusively on the XPS products pretty much. So a lot of the data that I'm going to be showing you in the next few sections of today's event has been collected either by me or my colleagues in the applications team based in our lab in a little town called East Grinstead, which is around about 25, 30 miles south of London. So we're based in the south of England. We're about halfway between London and the south coast. And we've actually been manufacturing XPS systems for over 50 years there. So the company started out was called Vacuum Generators. It was started by a guy in the garage of his house. He licensed the technology for conflat flange sealing from the Apollo program over here with NASA, and started making right-angle valves. And from that, he decided that vacuum systems are the way to go. At the time, interest in understanding catalysis was becoming important, and so he started developing instrumentation. And around about 1969, the first XPS system was created by our company. But Hewlett-Packard actually produced the first commercial one, but we were second or third. And now, from that sort of early beginning of a few academics being interested in, now we ship instruments all around the world. We don't actually manufacture in the UK anymore. Now we manufacture in a town called Brno in the Czech Republic, which is also where our electron microscopes are manufactured as well. And so for the next however long it takes to get through this section, I'm going to be talking about using XPS and other surface analysis techniques to look at metal and oxide surfaces. So there's all sorts of different things that we can use XPS to understand these types of materials. We can look at problems around the passivation of steel, so obviously preventing corrosion, very important if you're going to be using metal parts on or any kind of vehicle or building or in any device. And so one of the key things is understanding there's very, very thin layers that are deposited on the surface of a metal to prevent corrosion happening. And that was, along with catalysis, that was one of the first applications for XPS. So the two main ones that the instruments were developed for were understanding catalysis and understanding corrosion. The next one is contaminant identification. So if you've got an issue with how a part is behaving, then chances are there's probably some contamination on the surface. So we want to understand what that is. It's fairly easy to understand. And then James mentioned depth profiling briefly in the list of experiments. So how can we access where interfaces are between the layers and understand what's going on? And so that's where we can use the ion source on the system to probe deeper into the materials. And so we'll talk and see examples of how, quite a lot of examples during today, actually. It's one of the main experiments we do is looking deeper into the sample and understanding interfaces. And finally, if we've got some staining or something on the material, understanding the homogeneity. And so the first example, and this is a sample that is a temperature sensor it's actually for a domestic hot water boiler. So the idea is this should be a tube, and the water can go in here and interact with the thermocouple at the end here, give a readout, prevent the boiler from running too hot, and control the operation. And the problem with this one is you can see this kind of white staining here, and actually the tube is full of this white material. It's like concrete inside the part. And for this particular thing, I think this was number 3 of these that had been replaced on this boiler. They were lasting about 6 or 7 weeks and then having to be replaced. And the question was, okay, what's going on here? Why are we seeing this breakdown? What is this material? What's happening here? The engineer who was doing this was thinking it was maybe down to the hardness of the water, so that this was just precipitation of calcium carbonate out of the water, solidifying in the part and causing the problem. The issue was that the water where this was installed was extremely soft, so there was no chance of that happening. There wasn't any lime in the water to precipitate out, so it had to be something else. So we need to try and understand, and so we've got an area here where there's no amount of this material, and we've got an area here where there's lots of this material, so we can start doing some point analysis and understand what's going on. So I'm going to walk you through exactly how we would do an analysis of this type of problem. So start off, and as James has just been showing you, the way we start off any analysis is doing what we call a survey spectrum. And so this is going across the entire energy range of the instrument, and we get data that looks like this, and then we can start to identify the peaks that are present and understand what's going on. Now, James has just been talking about the importance of gloves, and actually even making sure that you don't touch the areas you're going to analyse with the gloves as well. Chances are this sample by the heating engineer was just handled with their hands. So we've got not just sort of carbon oils from their hands, but sodium chloride from the sweat in there that's on the surface as well. That's the sodium peak there. Chlorine's around here somewhere. And carbon contamination's affecting the results. Now, one of the sort of classic ways to tell this, and this is proper advanced level XPS now, so it's a bit of a trade secret, keep it to yourselves. The shape of these funny steps in the spectrum is actually quite diagnostic in telling you where things are ordered on the surface. Now, as I say, I've been doing this for 20 years. I know this is a carbon peak, and I know this is an oxygen peak. But after this peak, I can see the shape of this background is curving down like this. And behind the oxygen peak, I can see it's sort of curving up like this. And also, all these peaks here, rather than curving down, the background's curving up. Now, if the background's curving down like this, that means that the largest peak next to that is at the surface. And that's where I'd expect, but also now I've got confirmation the carbon is on the top. So this is going to be surface contamination. Everything else, though, I can see the backgrounds are curving upwards, and that means that the photoelectrons for these peaks are having to pass through something else, and so not all of them are able to escape from the surface without losing energy. And so these shapes of the backgrounds are because a lot of the signal is being scattered by hitting other atoms, other electrons in the surface, and losing kinetic energy. Remember, binding energy 0 to 1350 here, but kinetic energy, what we're actually measuring in the instrument, is 0 over here and the maximum over here. So the more we are over in this direction, the more slowly those photoelectrons are traveling. And if they're losing energy, then we'll start to see more of them here. So this curving down, carbon at the surface, this curving up, this will be the oxide on the surface of that metal, and that's underneath the carbon overlayer. So what we want to do is clean the sample to get rid of that carbon so we can actually start to understand what's there. And so we give it a bit of an etch with the ion source on the system. So this is using monatomic argon ions, hitting the surface, knocking off material very slowly. So we're removing material at a few angstroms per second. And as we clean it off, remember which way around this is. Yes, the red one is the new spectrum now. So you can see now the backgrounds are starting to curve down, and we can start to see some more peaks. So what was just this shapeless blob here, now we can see these peaks here. We can see this doublet here, some more peaks here, load of other little peaks here. This carbon peak is now much smaller. The oxygen peak's a little bit smaller as well. So what we want to do now is actually start to identify and quantify what's present. And the good news is the software helps you do this, so you don't have to remember all these peaks. So we just open up what we call our Enhanced Survey Processing, so ESP, and that gives us an idea of what peaks are present. So anything that's indicated in green, the software is saying it's fairly confident that's there. Anything in pink, it's not that confident about. And it's saying, okay, it might be there in very low concentration. And what you can do is just right-click on one of the markers in the periodic table, and that will put markers on the spectrum to give you an idea of what should be there, and you can check and see that if it's actually a peak or if it's just noise, and you could ignore it. So we can work through and check all these things, and we can see now we've got sodium, magnesium, calcium, nickel, copper, zinc, phosphorus, sulfur. The argon is there because we've cleaned the surface with the argon gun, so we've embedded some argon into the sample, so we can ignore that. That's something we've added. And then carbon, nitrogen, and oxygen. If we want to check, like I say, we can just right-click on an element, and we can just show that these peaks correspond to, in this case, a lot of these features here are due to nickel. These aren't photoelectron peaks. These are, as James was showing you in the cartoon of the atom, after a photoelectron's been emitted, we've left a hole in the electron orbital where it was, and that's got to be filled some way. And one of the ways it can be filled is by what's known as an Auger cascade. So another electron from a higher energy orbital drops down into there. That releases some energy, which causes a third electron to be kicked out. It's a 3-electron process, which means there's quite a bit of uncertainty in it. And so these are the Auger features for nickel here, and you can see they're quite broad because we've got the uncertainty in the energy of 3 electrons in there. So they can be quite diagnostic, and in a moment I'll explain for the zinc how we can actually use those. Okay, so we just measure the area of the peaks, and the software converts those into atomic concentration. So we can see differences between the clear and the contaminated area. If we look at the oxygen, we can see there's about a 4% difference between, and I've lost the top of the thing to tell me which one's which. So let's see. Yeah, the contaminated area is the one with the zinc, I think. So this is contamination, this is the clear area, and we can see where the contamination is. We can't really see the underlying nickel of the part at all. We can just, we don't see any of that. So it looks like this zinc is possibly the compound that's being formed, and we need to now investigate a little bit more to try and understand the chemistry and see if we can identify what it is. So this usually means going on the internet and looking around in various online databases. We do actually have built into the software something we call the knowledge view, which enables you to just say, show me the information for this particular element, and it will pop up a page and give you reference data, peak positions, information about how to process the data. If you want to look at this, you can find it. This link should work, although I've had a little bit of trouble with the redirect at the moment. But if you go to the thermofisher.com website as well and look for Material Science Learning Center, then you'll also find exactly the same content. This just redirects to the Material Science Learning Center, but it's a much shorter URL, so it's easy to remember. I don't think lasurface.com actually exists anymore, so ignore that one. But the National Institute of Standards website has a very comprehensive database as well of XPS data. And there's other ones as well. XPS fitting, I think, is another place where there's reference data online. So once we've identified the elements of present, we'll collect high-resolution scans. And so I've got some here for, these are the reference data from the knowledge viewer for zinc. This is one of those Auger features I was talking about. This is the core level for zinc. That's a typo, that should say 2p, not 3p. And then over here we have, from the sample, we have the zinc Auger and the core level. Now the core level peaks for zinc, for the metal and the oxide, James just showed you a range of chemical shifts for carbon and for iron. Unfortunately for zinc, it doesn't change peak position at all when you go from metallic zinc to zinc 2+, which you'd have in zinc oxide and other zinc compounds. However, we do see quite a big shift with this Auger feature. You can see over here in the reference data, zinc oxide looks like the green, zinc metal looks like the red. And so by comparing between our contaminated and uncontaminated surfaces, we can see that the zinc is in a 2+ state. We can look at the other ones as well. We can see the phosphorus is phosphate. We can see in the carbon contamination, we have a little bit of carbonate. There's a little bit of potassium there as well. And the oxygen, there's a couple of chemical states for the metal oxides and the carbonate and phosphate. And for the zinc, we've already established it's in zinc 2+. So what we need to do now is try and wrap all that information we've got and turn it into some sort of story to explain to this very important customer why their hot water system is. I should say this was my main funding source when I was a student was the supplier of this sample, i.e. my parents. And so they thought after spending all that money on my education, it would be nice to get some free analysis to understand what was going on with this particular problem with their hot water system. So the zinc phosphate is usually used as a corrosion inhibitor. So the surface is coated with this zinc phosphate layer, and that's to stop the hot water attacking it while it's being used with a sodium compound used as the binding agent. And unfortunately, this layer wasn't stable, and so it was precipitating out. It's not very soluble, and it does form a material that looks just like concrete when it comes out of the coating. And what they've been doing is not buying the parts for the boiler from the official supplier for the system. They'd be buying it from an unofficial third-party source. The coating wasn't being applied correctly. It wasn't being fixed to the surface of the sensor. And so that was causing the breakdown and the release of this compound in the water system, and it was just precipitating out on the surface of the sensor and causing the failure. Once it was swapped to using an official spare part where this zinc phosphate coating was applied correctly, then the temperature sensor worked perfectly, and my parents were able to enjoy their shower. So that was the thing. So it's a fairly simple example in terms of the sort of process we do. The experiment took maybe an hour or two to complete, so it wasn't a particularly long experiment to do. The steps that we went through were exactly that. We collected the survey scan, then we do the high-resolution scans to get an idea of what the chemistry is, and then we can then use that as the basis to try and understand what's going on. So it's XPS is a fairly quick technique on a basic analysis like this to understand a problem with a sample. Now, it can get a lot more complicated, and as we go on now, we'll see experiments where we have to do a little bit more work to try and get to the bottom of it. But before we do that, let's look at something that's a bit more related to this in terms of trying to prevent corrosion. And how we can use XPS to understand steel passivation and issues that might come when it's not being done correctly. So what we want to really do is understand the formation of typically the enriched chromium oxide layer at the surface of the steel and determine if that is conforming to the amount that's supposed to be there. So if we look at the iron surface chemistry and we look at a passivated steel surface and an unpassivated steel surface, this is the peak for metallic iron, and this is the iron oxide peak. When we haven't got the passivation applied, then we can see much more oxide at the surface compared with the passivated surface. And so there's the metal peak, and there's our iron 2 and iron 3 oxide positions, and predominantly iron 3 oxide when we've got the exposed surface. And what we can do then is measure the ratio of oxide to metal. So on the unpassivated sample, we've got 4.3 to 1 there, and we can also look on the passivated sample if we want to understand the ratio of iron 3 to iron 2 to metallic iron, then we can see that as well, but substantially less oxide here on the passivated surface. And if we look at the chrome surface chemistry as well, then not a lot of difference between the passivated and the unpassivated surface, because we're enriching the surface with the passivation process with chrome to try and protect it, because the chrome oxide is much more stable and protects the steel. And so again, we can do quantification of our chromium metal and chromium-3 oxide, and do the calculations to work out the ratios of the particular components and understand how the passivation process is working. Now, once we've done this once and we've got the recipe for doing the quantification and the peak fit, we can just apply that as an automated recipe. So if you were sat there and you had a bag of 20 of these samples to look at, mount them all up on the system, program in the analysis to do the peak fitting, and then just press go. And at the end, you'll get the software can report out into Excel and give you just a chart that says, okay, samples 4 and 6, passivation layer hasn't been applied correctly, all the others are within the control limits, and so we're okay. So that's quite easy to do. But say you have a sample where this layer is a little bit thicker, and so we can't actually do that measurement directly on the surface. So this is a real example of a sample that came into the lab where they'd got two steels that were supposed to be the same, and this one wasn't corroding, and this one was, and they were in quite a critical application, so they were going to be under quite a lot of stress, and having corrosion on these parts could cause a significant failure. So they wanted to understand the problem here. So we can obviously see optically there's a bit of a difference here, but that could just be, milling or surface finishing or whatever. It's not necessarily anything to do with the chemistry. And if we just have a look at the composition, largely between them, they look fairly similar. So the sample 8's the good one, sample 14's the bad one. And we can see there's a similar amount of carbon, similar amount of oxygen, maybe a little difference in chromium and nitrogen there, but nothing too much. And so what we probably need to do, again, these parts have probably been handled by without gloves or just where we're going to analyze, and so we need to clean them off. So we'll do a depth profile. And just to sort of show this in a little bit more detail than James did, so we're collecting our data from the surface, and as James said, that's 10 nanometers thereabouts, about 30 atomic layers. And we want to go deeper, so we want to understand in the layers below what's going on. And so the process we follow is collect XPS data, then we etch the sample with the ion source, so we'll raster over an area that's about 5 times larger than the area we want to collect our data from. And the reason we do that is we want to be collecting data from the flat bottom of the crater. If we have the etch area too small, then we'll be risking collecting data from the edges of the crater, and that will mean we won't get as good depth resolution on the data, so we might start seeing layers that we've already removed, and it will blend it in. And we just keep cycling, and as we do that, we quantify the amount of material we have, and that generates us a generally actually converted. This is a little bit tricky to convert into depth. Usually we'll have to quantify against a standard material and just say, okay, this is the etch rate we would have had on silicon oxide or tantalum pentoxide or some other material that we can easily grow a known oxide thickness on. It's very rare you can actually get good standards of the materials you're etching. It's the question we always get, and I'm sure someone was thinking about it as I was going through this, is, okay, how do you relate your thing to depth? And it's tricky, is the answer. Everything etches at different rates. If we can get standards and measure them, or if we can cross-section the material and check it with an SEM, then we can use that to do it. Otherwise, we have to just apply and say that we've got an etch rate that we know against a known standard material. And we carry on and build up our profile. So this is the profiles from the two steels. This is the good one over on this side. This is the bad one over here. And the first thing we can tell quite quickly is they're quite different. So the first thing, whether they are the same, is this line here that goes down and this line here. That's the carbon being removed from the surface. So as we remove the carbon, then we start to see other signals coming up. And on this sample, the signal we see coming up most quickly is and all these colors unfortunately look a bit the same on here. We see chromium and we see oxygen. And so that's our passivation layer on the surface of this steel. However, over on this side, what we see coming up is actually the underlying components of the rest of the steel. So it's not the chrome we see coming up immediately and forming that barrier layer. We see the molybdenum, we see nickel, we see the iron, the chrome. So we're seeing all the major components of the material. And that's what we see over here. Once we get through that passivation layer, we don't see it on this side at all. Now, colleagues in the electron microscopy group had been looking at the same sample as well, and they wanted to look at this very thin layer. So everything's happening within the first 30 nanometers or so of the surface. And so the way they would look at that is put it into a fib system, cut a cross-section, take it and have a look in the TEM and do it that way. And that's quite a time-consuming process. Whereas to do this took 20 minutes. And so we were able to get an answer considerably. I know it's not a competition with our colleagues in the other parts of the business, but it is. And so that was the thing. So it's a really efficient and easy way of understanding these types of materials. And again, you can reliably set this up as a process. We do have customers who do a similar kind of thing on contact lenses. So they want to check that the hydrophilic coating that you apply to contact lenses to stop them being really unpleasantly uncomfortable has been applied correctly, and they'll take samples from different positions in the plasma coater and then do exactly the same process as this and do these depth profiles on hundreds of lenses. And then as long as they fit within a control chart, you can understand it. So for steel, for looking at these passivation layers, if they're thin enough, we can do it just directly, just looking at the surface and calculating the ratio of oxide to metal. If it's a bit thicker, then we use depth profiling to etch through the samples and determine the differences and understand why we might be getting failures. Okay, contamination. So this is an example where we're looking at a dental implant. So this is one of the fixing screws for attaching a tooth into the jaw if you've had one removed. And what they want to know, obviously, is whether the cleaning process before it's packed up and sterilized to go into the usage has been successful. And this is the screw here. So we've got the tip. Then the root is the section between the threads, and the crest is the top of the thread. And then obviously up at the head here is the fixing where the part would be added on at the end. And so what we want to do is use XPS to analyze different spots on the material to check and see whether there's any residues from the production process there left on the surface. So we've got the root, the crest, and then near the head, on the side of the head, and the tip at the opposite end to the head on the thing. And we can see various different elements present. Now, it's supposed to be titanium, and nearly everything else that is there shouldn't be there, basically. Well, actually, the copper and the zinc is supposed to be there. Molybdenum isn't. Carbon, obviously, is a ubiquitous contaminant, so we'll see that pretty much everywhere. And from those survey spectra, again, we can do what we've done every step so far, and we can do quantification. And so the important ones where we want to look, we're seeing differences between the crest and the root. So we want to investigate those a little bit further and see what's causing these differences in composition. And near the head, we're also seeing some evidence of molybdenum being present and some sulfur, and understand those as well. So firstly, looking at the around the head of the screw. So titanium metal, we can see a little bit of the metallic signal. It's mostly quite oxidized. And then in the molybdenum region, we can see also sulfur, peaks for molybdenum disulfide, and some of that presumably is a little bit oxidized, so we can see molybdenum oxide as well. Now, molybdenum disulfide is quite often used as a lubricant. In various cases, we use it on the UHV systems because we can actually put it in vacuum and it doesn't cause us any problems. And so this looks like it's not quite been cleaned off the part after machining. If we look in the shaft and in the crest and root regions, in the root we can see quite a lot of chlorine in two chemical states, both organic and metallic. So we've got some chloride present and some organic chlorine, possibly again left over from cleaning if it's been solvent cleaned and not been completely removed after that. And in the oxygen, we can see less contamination in the root compared to the crest. Now, this is probably actually just due to the handling of the thing. If you think when you're picking these up, you're going to touch it on the crest rather than the root. So I suspect seeing more of this oxygen and carbon contamination there is probably just due to handling, or even in the packaging that it's been in, rubbing against the plastic, it will pick up more of the plastic contamination on the surface than it would in the dips in the screw. And so we're able to analyze different areas quite easily. One thing I would say, actually, it was quite deliberate that we mounted the sample in this direction so that the threads were running this way. The X-rays on the Nexa and K-alpha instruments, so the Nexa is the one that's here at NIAR, the X-ray source comes in from this direction, and so that means we could access all the areas on the sample. So you do have to consider the geometry of the instrument. Remember James showing you that schematic of how all the sources were arranged in the analyzer. You need to consider that when you're trying to do experiments to make sure that the sources can actually access the part you want to get to. So if you've got a really, really thick sample, you don't want to put a really thin sample behind it so that the X-ray source can't access it. And so you do have to make a couple of considerations when mounting samples on what you want to see. Okay, let's have a look at some imaging now. So we've just done point analysis so far, and we've done a little bit of depth profiling, and the last type of XPS experiment is some imaging. So we've got an aluminium part here. Again, I think this came from a car radiator, and we've got some discoloration just up here in this top corner. It's aluminium, or aluminum, seeing as I'm over here, and what we want to try and understand is, okay, what's the nature of this contamination, this discoloration in the top corner, and try and establish what maybe is causing the other differences. So you might just be able to see it's a bit lighter here and a bit darker here. See this dark area, light area, and then the brown area up here is the discoloration. So we can easily, obviously, optically see these three areas. This looks a bit like a patchwork because it's actually quite larger than the field of view, so the software has just tiled together images for our area. And first things first, do some point positions and collect a survey scan to understand which elements are present. So we have our, that's the button. We have the light grey area is the green spectrum, the brown area is the blue, and the dark grey area is the red one. And the light and dark grey ones look pretty similar. There's not a huge amount of difference there. And obviously there's a big difference with the brown area where we can see lots of iron present. When I said the brown discoloration, probably a good guess would have been some iron oxide there on the sample. So that's what we can see. We also see a little bit of zinc there as well. And so we can now quantify all those elements and establish how much we have. And so we can see in that brown area, really, over 10% of iron presence and about 7% of zinc. So, but apart from that, not too much difference. But what we are seeing lower aluminium there, obviously, with the coating of this contamination. So then we can map the surface. So this green rectangle here is the indication of the area that we mapped. The little ellipse at the top here is the size of the X-ray spot we use to map it. So that's, to give you an idea of the scale, that spot is 150 microns. And so we do a 150 micron step between pixels in the map so that we don't get overlaps. And we don't map for everything. So we'll do those survey scans first so we can choose the regions we want to map for, so that we don't spend ages. I mean, you can do a survey scan at every pixel, but it takes a lot longer. It's a lot faster if we can use what we call our snapshot acquisition mode, where we can collect a spectrum in, instead of maybe a couple of minutes, we can collect a spectrum in about 2 or 3 seconds, and so that we can speed up for something like this, where we're going to have a fairly large array number of points. If we do minutes per pixel, it's going to take days to collect the data. If it's seconds, then we're going to have the image in an hour or 2. And actually on the, this is quite an old example. The system here now has our new image acquisition mode we call SnapMap, where it can collect an image in a minute or 2. So it's even much faster way of operating. So these are the images. So this is the one for the alumina, aluminium oxide. We can see distributed there. This is the iron here. Oxygen we can see is a little bit elevated over here where the discoloration is. Chlorine, we can actually see this, which is invisible optically, but we can see an accumulation of chlorine here. I suspect because it's associated with the sodium, this is where someone had touched the sample before handing it on to us. So again, I'm going to keep saying gloves through it, but yeah, sodium chloride present, if it's not expected there, is usually the indication someone's touched the sample. The zinc, interestingly, is just really strongest on the edges as well. So that's possibly where a fixing has been for the piece, and it's just there's some sort of abrasion there, some scratching, and it's transferred some material from the fixing. And then what we can also see is there's a concentration of sulfate. So there's some SO4 present around this area here. So it's possibly even strongest in this dark area. That aluminium sulfate form there might be the reason why we're seeing that discoloration at that point. And probably what we'd want to do is actually start depth profiling through here to get an idea of how thick these contamination layers are, whether it's actually penetrated into the material or whether it's just a surface issue and disappears quite quickly. And we can also, just to confirm things, overlay the XPS data onto the optical image. So get these nice color plots and showing the locations of the different components. So chloride there, aluminium oxide here. We can see that sulfate is overlapping with the aluminium here, and then the iron over here in the staining. So again, by using the imaging, we can look at the distribution of these chemistries across the surface, identify things that we couldn't see optically, and also confirm, what we suspected about the dark staining on the material. Another area where we can use the imaging and also just the chemical state identification to look at the surfaces through looking at tribology samples and seeing how the layers that are applied to try and prevent wear on the surfaces change chemically through the lifetime of the part, and understand if you've got problems between where it's not working quite as well as you'd hoped, and you're starting to see all these scratches here, whereas on the good sample it should be nice and smooth still. Try and understand the reason why that coating isn't working the way it's supposed to be. So this is a sample that came from a group that we're collaborating with in Austria, and it's been coated with zinc dialkyl dithiiophosphate, which I'm going to call ZDDP for the rest of this. As I say, they're seeing different levels. So this is an old sample which was good, but just has been exposed to the testing for a long time. These two have had the same amount of testing One is showing good wear resistance, one is showing bad wear resistance. So we want to understand whether there's a reason why that is. Again, first step, let's get a survey scan and understand what elements are present. And so we can see here, we've got phosphorus, sulfur, chlorine, carbon, calcium, oxygen, fluorine, iron, zinc, sodium, and magnesium. And we can see differences in the amounts of these in the 3 different samples. So the zinc level is a bit higher in the old sample. If we look at the calcium level, we can see that it's highest in the old, it's about halfway in the good, and it's very low in the bad. So that could be an area to investigate. And the carbon levels are quite different as well. So these are elements that we'll maybe focus on to investigate to try and understand what's going on with the sample. So let's have a look at the carbon region. And what we can see, in the old sample, we've got 3 chemical states. We've got this one here, which is the hydrocarbon. We've got some carbon single bonded to oxygen. And then this is a peak due to carbonate. And if we look at the 3 samples, we can see quite big variations, particularly in the carbonate concentration. And actually in the bad sample, it's not really carbonate, it's actually more like an ester type functionality. So we can see those differences there and understand that this carbonate should be present at the surface, and in the bad sample, the one where we're seeing wearing, we're not forming that surface. So is this true across the sample? Well, we can start to investigate into different areas. So we can look on the tops of tracks and in the tracks and see again variation. Even on the old sample, the amount of carbonate in a track or outside a track is kind of different. And then by mapping it, we can just look at the distribution across it. So again, on the old sample we can see the variation in the iron signal and the carbonate, and the iron versus the calcium. So we can see the calcium and the carbonate signals overlap. So that's giving us a good idea it's probably calcium carbonate that is there. We can also actually measure the thickness of the calcium carbonate because it's thin enough that we can see the substrate signal underneath it. And so what we do is by looking and using the software to calculate how much the signal from the substrate is attenuated by the overlayer, we're able to use that to calculate the thickness of the overlayer. So if, in this case, we've got the calcium carbonate, we know the density of it, we know its electronic properties, and so we're able to look at the signal from our iron, and we know its kinetic energy, so we know how easily it will transfer through the material as dense as calcium carbonate, and we can use that to calculate the thickness. So we can see it varies from 4 angstroms to 87 angstroms, so about 9 nanometers in the thickest areas on the surface here. And James mentioned earlier on about angle-resolved XPS, which is one way that you can do this when you've got slightly more complex systems. But when you've just got a very simple A on B overlayer on substrate 2-component system, you don't have to do the tilting experiment. You can just, as long as you can see the signal from the substrate, you can directly calculate the thickness of the overlayer, which is really quite useful. If we look at the good sample, we can see again the calcium carbonate, and again it's a little bit thicker here, even here, so going from about 20 angstroms up to 100 angstroms, and again we can see that distribution of the calcium carbonate. So iron should be red, I think, and calcium's blue, and green and blue here, and again clearly defined tracks of the calcium carbonate. On the bad one, we just don't see any calcium carbonates, and the mapping experiment's a complete waste of time. And so that's what it is. Way they apply the ZDDP on there also has a kind of calcium detergent they use to apply it to the surface. And if that isn't applied in the correct ratio, you don't get this carbonate forming, and that causes poor wear performance on the material. So with our clearly defined tracks of calcium carbonate being formed during the wear testing, we get good performance. If that isn't there, and that ratio of ZDDP to calcium detergent isn't correct, we get bad performance and we don't see the right wear characteristics on the part. And so again, detecting these very thin layers, remember we're looking at less than 10 nanometers of calcium carbonate on the surface is determining the performance of this, this part in the, once you've actually got it working in an environment where it's going to wear. Okay, this is the last example before we can all go and have a cup of coffee. I see the celebrations. So this is a kind of quite unusual sample. It's a very, very complex, multi-level metallic stack. And they're probably all deposited by vapor deposition onto actually a polymer substrate, which links quite nicely into the next section, which will be about polymers. So there's quite a lot of technology involved in preparing this sample, which is kind of interesting because the actual material itself is pretty cheap and everyday. It's gift wrap for parcels and things like that. It's that sort of metallic, shiny stuff that you might wrap things for Christmas or birthdays and things like that. And it's delaminating a little bit. So what we want to do is look at the layers and try and establish where it's breaking down. And to do that, we've got to try and understand what the layers are, because we don't know exactly what elements we have present. So this is a 3D plot of profiling into, so we're using depth profiling, we're etching into the sample, so the etch time is along this axis. So this is the surface, and this is deeper into the sample. And as we go from the surface, we start off and we see titanium oxide, and then we go through, we see a bit of nitrogen, there's some aluminium, some copper, carbon, and so on. So once we know what's there, and we've done this experiment quite quickly, we can then collect high-resolution spectra and build up a chemical state profile of the sample. And what we actually find is that to make this gift wrap look this particular color, I think it was a quite sort of emerald green color from what I remember, with a little bit of other sort of colors shimmering underneath it. We have titanium oxynitride, titanium nitride, titanium oxide, aluminium oxide, an aluminium and copper alloy, aluminium oxide, aluminium and copper, aluminium oxide, and then the polymer, which is quite a lot of work really for just making some gift wrap, which is going to be wrapped up, torn up, and then thrown away. And this is what the depth profile looks like. So we've got concentration here, etch depth here. This is the polymer over on this side at the end, and then we have all these different layers. You get similar kinds of profiles for hard disks, and we'll see a couple of others for different situations that look a bit like this later on in the day. So we can look at the delaminated area as well. So this one is the actual real sample, and then if we look at the delaminated area, oops, we can see that we don't get quite the same profile. And so we can see here by the layer that we're coming in at here, obviously there's going to be a little bit of, this is oxygen, we can see this is the aluminium oxide, so it's one of the aluminium oxide layers where the coating is breaking down. And so by putting the two profiles on top of each other, so the dotted one is the delaminated area, the intact area is the solid lines, and we can see where the break occurs just by putting them on top of each other. Because we're using the same etch rate, we know that the etch rate through the sample is going to be very similar, and so we can see that this is where the coating is breaking down. And so just by doing a initially survey scan, depth profile to identify the elements that are present, then doing depth profiles to identify the chemistries that are present within the stack. And then by looking at the intact and the delaminated areas, we were able to identify exactly which position. Obviously, we had several aluminium oxide layers. We needed to know which one was the point where it was breaking down, between which two layers was causing the delamination failure. And by doing the depth profiling experiment, we were able to identify very easily where that break was occurring and separate out the differences. Okay, that's all I'm going to say about metals and oxides at this point. Are there any questions? Yes.
Depth profiling, how do you get a sense of how deep you've actually gone, and how do you control that you're not sputtering your material?
Well, we are always sputtering the material somewhere else, so it's a good point actually that you do have to sort of control the way that your system is aligned and arranged so that you're not directly sputtering the material off the sample and coating some other part of the instrument. I mean, generally, because you're removing quite small amounts, the particles are just pumped away through the vacuum system, so we don't see them building up somewhere. In terms of actually determining the depth, what we usually do is either take the sample out after we've done the depth profile and put it into a profilometer to measure the crater, and then we can get an idea of the average sputtering rate, although you do have to always consider that those materials will sputter at different rates through the process. The other thing you could do is cross-section the material and just actually directly measure it in an SEM if you can resolve the layers, if they're thick enough to be able to resolve in an SEM. Or there is a way of using that process I was talking about using the overlayer calculation. So as you get to an interface, you use the overlayer calculator to determine the thickness of the layer as you sputter through it. And so you can work out then how much etching relates to removing that material on the interface. As you can see, the layer below and the layer above, and you can use that to calculate the etch depth as well. But it always is a little bit of an approximation, and we tend to just put in a average depth. So the depths are, of the stack is probably correct. Of the individual layers, there will be an error on them just because of the nature of the sputtering process. Yes. Yes, so the intensity of the signal is determined by how easily we can get the photoelectrons out into the analyzer. So the X-rays, although they're not very energetic X-rays, we're only using soft aluminium K-alpha X-rays, they still penetrate a few hundred microns to millimeters into the sample. But the photoelectrons can only travel, as James said, about 10 nanometers or thereabouts. So if you do have a rough surface structure, then you may, if that's the electrons are coming straight up into the analyzer, so if there's overhanging bits and that might attenuate the signal. Now that can be a problem for the intensity, and you would see, if you were looking at the raw intensity scale, variations in the peak intensity as you look at it. But when you actually calculate the atomic percent, because everything has been attenuated the same way by the roughness of the surface, the actual composition you measure is independent of that surface roughness. So in most cases, it doesn't matter too much unless it's really gross roughness of the surface. So where you are, I mean, typically if you're blocking the X-ray actually reaching a point completely, so it's traveling through a few hundreds microns of material, that might stop you seeing it at all. But if you do see the signal, then generally you can kind of average out problems of roughness. But it is something you do have to consider, and it may be that you actually put the sample on a turntable so that you can rotate it and try it in different directions to just make sure you're getting consistent composition. Do you have a question as well? Generally, we don't, and the reason for that is that when you do a solvent clean on something, you might leave a lot of solvent residue as it dries on the surface. Now, if something is grossly contaminated with something that we definitely don't want to put into the vacuum system, for example, then we will do a solvent clean on it and just give it a wipe with usually IPA or something like that that's not too aggressive, and then put it into the instrument. But generally, we tend to analyze samples as they come in and then just use the iron source to clean off any contamination at the surface. But if they are, if it's just come from an engineering site and it's covered in oil and stuff like that, then yeah, it's going to need some ultrasonic in or something before it goes into the system. Yes?
I was wondering if you tested like acetone, like making parts from acetone and then ethanol, high grade. I was wondering which one probably more contaminants behind.
Yeah, it depends. It very much depends on the material you're cleaning it. Acetone's pretty good actually, but we don't tend to use it too much just because it can react with things in certain cases. But the reason we usually use it is if someone in my group has left some of the double-sided carbon adhesive on the sample holder for too long, and it goes from being really easy to peel off to being like concrete, and then you have to use acetone to clean it off. But generally, we tend to just use isopropyl alcohol for cleaning samples or sample holders because we just want something that's really not too, we don't want that risk of any reaction really at the surface, and it's quite easy to wipe it off and not leave any residue on the surface. Ethanol's usually pretty good though as well. It's just that IPA is a little bit more safe to store around the lab.
Everyone, I think so. I didn't introduce myself and first in the morning. I know some of the people already, but some are new faces. So my name is Manish Shinde. I work in the NIAR Advanced Coating Lab, and I handle the coatings department. So we do a lot of coating-related testing, adhesion testing, and with the new addition of XPS, we do even characterization and analysis. So any kind of adhesion failure or part defects, manufacturing defects, we can basically start working on different analysis now. So today I've got some part of the presentation where the industry has provided some samples to us to analyze and see what type of defects and if we can find some answers to it. So whatever I'm going to present are actual industry parts that industry has submitted to me. Okay. So for the metal section, there are going to be basically pretreatment defects, Cr6 and Cr3 identification, and phosphate anodizing defect, and additive manufacturing metal powders. So the first part is basically a steel phosphate. So if you can see on the top section, whenever a phosphate anodizing for steel, when they do the processing, they basically hang the part out, and at the bottom, they are finding this kind of a defect where they have some kind of an accumulation. So initially, they didn't understand what was going on. So this was one of the parts that they sent us for analysis. So in this, we found one of the spot has basically an iron oxide that is basically spread out, and it got distributed all over. So this particular part is just focusing in this particular area. You don't see a very spot because it's just so small, it's visible, not easily visible. And, go back. So this was showing an iron and the oxygen. Basically, there is iron oxide focused in that particular spot where there was error, and then it got a little bit spread out. So we have a little bit iron spread out, and phosphate, again, there is less concentration on phosphate in that particular area and more phosphate on the other region. There is a combination of map that include all the phosphate, calcium, oxygen, and some silicon. Silicon, I believe, is just a contamination by sample handling. And calcium also might be one of the process. So we still, that's the initial analysis that what we have found. The next sample is hexavalent chrome. So one of the samples that we received, as you see on the right, this is a microscope image. So we have spots, and there's ununiform distribution of the chrome. So we have, like, one spot has a higher concentration. Just by visually looking at it, you see a yellowish spot, and one area you don't see anything. So the question was, do we have a chrome uniform deposition on the metal pretreatment or not? So this is the area basically we analyzed. On the projector, we can't see it very clearly, but if you look at under a regular computer, this is the area where you find a lot of yellowish, and this area is basically less metal deposition, or it's just more metal finish. So the chrome, we basically identified there is Cr6 and there is Cr3. Initially, we did a lot of initial test parameter, and Cr6 is so reactive, it's even reacting with the flood gun electrons that we are putting on the surface. So we're always constantly getting Cr3. Luckily, we had a software update just a few days back, and that helped to analyze the sample, and where we were able to detect a Cr6 now. So that's basically identifying your Cr6, and that's your Cr3. So on a whole distribution, you can see the Cr6 distribution and a Cr3 distribution. So there's a possibility that the Cr6 has been converted to Cr3 in some of the areas where is less deposition visibly what you can see. So this is just an initial analysis. This is what we found, and that's what I'm showing you right now. The other aspect is an overall map where we have some silicon composition. Again, it might be just material handling because this sample was just got it, and I'm assuming some kind of oil was on the material. So that's why we're detecting silicon. The other aspect is basically a Cr3 and Cr6. That is a distribution that what you're seeing overall. And the oxygen percentage. So that is a combination of map what you're seeing. So this is one of the defects. The next aspect was a phosphate anodizing defect. So on the right, you see this part. In the phosphate anodizing, they found this darker phosphate that they couldn't understand what was going on. So this part, they wanted to see what kind of defect they were having. So with XPS, again, we were able to find out. So we have a phosphate very highly concentrated on the left-hand side and less concentrated on the right-hand side. In the image, you won't be able to see much, but there is a slight distribution of aluminum oxide as well on this. Now, I've not shown that picture here because we didn't get a good image to show a presentation. But your center point where you have that defect, we have nitrogen, sulfur, and sodium. That's a definitive contamination. So your sodium hydroxide is sometimes used for etching process, and sulfur acid also is used in the process. So while they were rinsing the part, I'm assuming that they have not cleaned it very thoroughly, and some part I must have basically left out, and that's where we basically are finding sodium and sulfur and nitrogen. So this was a very good example of defect for an phosphate anodizing. So any kind of pretreatment, this gives a good example for industry of defect analysis. The next aspect is the additive manufacturing for 3D printed application for aerospace industry. Some of the industry is trying to reuse the metal powder after 3D printing. So we had run a study to find out what kind of oxidation level occurs from initial level to a 20 build cycles or 30 build cycles. So what's the objective of an oxide? Why do we care in 3D printing? In 3D printing, the major aspect is defects, small defects, micro defects. If the oxides in the laser, normally it gets completely removed, so you don't have to worry much. But if the oxides are way inside in the part and it gets trapped, that will create defects in the part. And that reduces the product overall performance. So we did basically analyzed the parts, and we were able to identify different titanium oxide and titanium metal. So we were getting a good amount of titanium oxide all over. And again, for aluminum oxide as well. So less amount of aluminum metal. As James must have earlier pointed out, if you compare an SEM EDS and XPS, XPS is going to give you just at the first 10 nanometer. So the powder is, let's say if it's 3 micrometer, you're just going to get the surface of the powder. So that's why you're going to see a lot of oxidation on your powders. So that's what we are basically analyzing and seeing the powder at initial stage and a later stage. So this is another for metal oxide and aluminum oxide showing the percentages that are just showing there. And vanadium has almost 3 to 4 different states that we have found. Again, vanadium percentage was very low. That's why we have a little bit noisy data, but it was definitely present throughout the study. This was a comparison on your bottom scale. You will see the build cycle 1 to build cycle 9. So there were 9 build cycles. So the 3D printing part, they basically accumulated the powder close to the laser and basically trapped it and basically provided that sample to me at a later stage. And we basically analyzed after 3D printing, close the powder next to the laser, how the oxidation basically affects. So they had done 9 build cycles, and the 9 build cycles are basically shown here. So in here you have metal oxide that is constantly increasing over time. So if you have to use a metal reuse, there has to be some kind of parameter or cleaning process or some other heating process needs to be done if you want to reuse. But again, there has some already published papers in the industry of reusable powders and what it affects. Because if you have more oxidation, your laser power also is going to be high. For titanium, again, we are seeing a consistent increase, but at some point it basically leveled out. So at around 30% weight percent. Then you have aluminum oxide. We have got some variable results from metal to metal aluminum oxide, slightly varied overall, but its tendency is basically constantly increasing after every build cycle. Again, vanadium overall, the percentage has been consistent because of the whole alloy is already at a very low percentage. So didn't see much of a difference from one point to another. But again, we are seeing multiple states. Vanadium metal. So initially, some of them, if you yellow bars, with build cycle 6, we were able to see it. But after the build cycle 7, we are not even able to see the vanadium completely. So it's basically any vanadium that we have seen is basically all on oxide layers. The another aspect that we need to further study is basically we are seeing nitride. So the nitride, we need to understand if it's a state with titanium nitride or it's a different state. That's a further study we have to basically observe. But we have seen a nitride state consistently throughout the process from start to finish, except one of the sample was showing higher for some reason. So again, these are just metal powders that are used for 3D printing application. Okay. So I don't have a lot of slides because this is industry sample, so I'm going to end it here. And then, Tim, James, do you want to now go over, or do you want me to cover the polymer small aspect of it?
You want us to start that polymers now?
We can start the polymers now if you want to. Okay. So, okay, I'll forward it to Tim for polymer aspect. James, okay. James going to show it, and after him, I'll show you some of the peak samples and fiber UV degradations. Okay. All right. Thank you.